Hi everyone! In this video, we look at the elimination of alcohols in acid. Why is acid necessary for this reaction? Well, let's consider this reaction scheme and two questions. One, are the best leaving groups strong or weak bases? And two, is OH- a strong or weak base? Our leaving group is hydroxide here. And hydroxide is a strong base. We know this because its conjugate acid, water, has a pKa of 15.7. This is greater than 11, and acids with pKa's greater than 11 have strong conjugate bases. So what can we do to make this reaction work? Well, we can use acid. What do acids do? Acids protonate, and a protonated alcohol will leave as neutral water. And water is a weak base, a good leaving group. This scheme here is a great overview for this reaction. An alcohol is treated with a strong acid, like sulfuric or even nitric acid can be used. A beta hydrogen and the alcohol group are eliminated to form the alkene and water. The choice of acid is very important here. These acids, sulfuric and nitric acids, have non-nucleophilic conjugate bases. And this means that a competing substitution reaction is not possible. This anion is delocalized over 3 oxygen atoms in this structure. Whereas if we used something like HBr and we had Br- in solution, Br- is a good nucleophile and could lead to a competing substitution reaction. So it's best to use an acid with a non-nucleophilic conjugate base. This reaction is often heated. We indicate the reaction is heated by using the Greek letter delta, and it's heated to distill off the alkene product and drive this reaction to completion according to Le Chatelier's principle. This reaction proceeds fastest with tertiary and secondary alcohols. Primary alcohols are not practical to dehydrate by this method because of rearrangements and the reversibility of the reaction, leading to undesired byproducts. Let's take a look at a few pieces of experimental data to further understand how to predict the products of these elimination reactions. In our first example, we have a secondary alcohol. This alcohol is treated with sulfuric acid and heat. This will lead to an elimination product. And it turns out that the major product isolated from this reaction is the one shown here. What do you notice about this product? Yes, the carbon skeleton is different. There has been a rearrangement. Rearrangements are quite common for secondary alcohols. Of course, we can get elimination to form the terminal alkene, as well as elimination prior to rearrangement. But these are both minor products. In the second example, we're dealing again with a secondary alcohol with strong acid. There are 2 beta hydrogens here, and these 2 beta hydrogens mean that there are 2 possible elimination products. We could eliminate to one side to get the monosubstituted alkene. We could eliminate to the other side to give the disubstituted alkene. And this disubstituted alkene also exists as its stereoisomer. So we have the E alkene or the Z alkene. In this reaction, we isolate the E alkene as the major product. The Z alkene and the monosubstituted alkene are minor products here. Considering these data, which of the following statements are true of the dehydration of alcohols reaction? These reactions are regioselective. The more substituted double bond is the major product in these types of reactions. More substituted alkenes are more stable because of the inductive effects that stabilize the more electronegative sp2 hybridized carbons. These reactions are also stereoselective. In the example below, we see that the E stereoisomer is produced in excess of the Z. This is again due to stability, where we have these two alkyl groups far from one another that minimizes the steric interaction between those two groups. Chemists have proposed a mechanism to explain these experimental observations, and we'll study that in a separate video. Thanks for watching.